Welcome to Ready to Derive. In this video, we'll be exploring transformations of parent functions, these 6 in particular. So a linear function, absolute value, a quadratic, cubic, square root, and cube root. We will first of all begin by reviewing these 6 and how to create the graph of the parent function, and then we will get into transformations, these in particular. So you may recall that A represents a vertical stretch or compression, and if A is negative, you also get a reflection of the x-axis. H represents a horizontal shift, and K a vertical shift. You will notice that horizontal stretch compression is kind of absent from this study, and that's because if there is something going on horizontally, it can always be factored out of the function and turned into its equivalent vertical stretch compression. So it's not really necessary to treat horizontal stretches and compressions. We will do lots of practice and learn lots of neat tricks for graphing transformed functions. By the end of the video, we will be doing some speed graphing with which you can greatly impress your peers. So stay tuned until the very end, and without further ado, let's begin. So we'll begin with the most primitive, the most basic of all parent functions, which is the linear function. So y equals x, and any equation of a line, y equals 3x minus 2, etc., is just some, effective transformations on this basic line, y equals x. So if we fill in the table here, y is just equal to x, or f of x is just equal to x. And if we graph this, it's pretty easy to see that it just is a straight line, a diagonal, perfectly diagonal line. All right, the next parent function is the absolute value of x. And so if we fill this table in, very similar to y equals x, at least here, here, and here. And the only difference, all right, so like in this region here, everything stays the same. And the only thing that changes is when x is negative, it's almost like this segment here breaks and faces upward. So it's 1, 2 here. Let's have a look at that. So this part looks identical to y equals x, but when x is negative, all the y values become positive. So that's absolute value of x. Now, x squared, the parent of all quadratics. So 4, 1, 0, 1, 4. And if we graph that, you see that these 3 points here stay the same as for the absolute value of x. So if you didn't sort of sketch enough points here, you might be fooled into thinking you connect with straight lines. That's why it's important to kind of go 1 extra point on either side. And I want you just to pay attention a little to this point here, 0, 0. Notice that they all share this. Well, in fact, they all share 1, 1 as well. But I'm going to refer to this point here as the pivotal point. So for y equals absolute value of x, that's the vertex, also known as the vertex. And for x squared, it's also known as the vertex. But I'd like to just generically call this point the pivotal point. For y equals x, we can see that it's actually a point of symmetry. So if we spun that line around, so if we took that line and spun it 180 degrees, it would just land on itself. So I'm going to refer to that as a pivotal point, and you'll see as we engage in more complicated transformations, the pivotal point will help us to graph efficiently and easily. So the next parent function will be f of x equals x cubed. So if we cube each of these, let's see, and then we graph that, we have 0, 0, whoops, I guess change the color, 0, 0, 1, 1, negative 1, negative 1. Was if we stopped with only those 3 points, we would be kind of confused as to what its shape is. So important to go out just a little bit extra to 2, 8, and negative 2, negative 8. And this is our cube, y equals x cubed. So let's go on to y equals the square root of x. Now, in this case, the square root of negative 2, we can't do. Square root of a negative, we can't do that. Square root of 0 is 0. Square root of 1 is 1. Square root of 2 is a decimal. It's kind of annoying, so I'm just going to make that 4, because I know the square root of 4 is 2. And then when we graph that, we have 0, 0, 1, 1, 4, 2, and the next I could do the square root of 9 is 3, just to give me a little more clarity there. And finally, the cube root of x. And I've tried to keep the table the same to show that sometimes you've got to sort of modify it to make it work. The cube root of -2 is a decimal, so I'm going to change that to -8. And the cube root of -1 is -1, 0, 1. I'll change that to 8 as well. And that's going to be 2. So you can see that, of course, these two here, this x cubed and the cube root of x, they're just inverses of one another, so x and y are switched. And let's just graph that. So 0, 0, 1, 1, -1, -1, and then -8, -2, and 8, 2. So we've got this. Those are not asymptotes, by the way. That's just growing very slowly. And in all these, let's identify the pivotal point again. It's going to be 0, 0 for all of them, but for different reasons. So here, it's a point of symmetry again. Here, it's just the starting point of the function. The function doesn't exist beyond that, to the left of that. But so 0, 0 is a very significant point in this case. And then here, it's a point of symmetry once again. So first of all, we're going to take an example and look at one of the parent functions, absolute value of x, and how it is influenced by these numbers, the 2. We know that's a vertical stretch, but why is that the case? -3, and here is a horizontal translation to the right 3. Why is that? We'll see shortly. And the +4 is a vertical translation up 4. So we're going to look at this, kind of build this function up, and then have a way of sort of shortcut of going about graphing these functions. So let's take y equals the absolute value of x, the parent function. And here's the table of values, and here is the graph. And what is the pivotal point here? The pivotal point is the vertex 0, 0. And in some ways, why is that important here? It's actually the lowest value that this function, that y, takes on. So the pivotal point is 0, 0. And I want to start by looking, we can do the vertical stretch or the horizontal translation first. I'm going to start with the horizontal translation so that we can understand where the graph moves. Now, the lowest, if we think about the pivotal point or the vertex being the lowest point, you have to think to yourself, well, what is the lowest that this quantity, absolute value of x minus 3, can be? Well, it can never be negative. So the lowest it can be is 0. So the lowest possible value of y is 0. So we know that's the y coordinate of the pivotal point. And then you have to ask yourself, well, what value of x will make the absolute value think that 0 is its input? In other words, what will make this whole quantity equal to 0? And that's x equals 3. So that is why we have a shift to the right 3. In other words, if I was to think about it, instead of 0 plugging into this new function isn't going to give 0, but 3 minus 3 will give 0. That works. And that means that we add 3. So in effect, what we do is add 3 to each of these values. So this becomes 2. -2 plus 3 is 1. 1, 2, 3, 4, 5. And it's like these are our new x values, so that paired with our other y values. So let's look at what this looks like if we graph these. We get the orange graph. So that clearly shows it's a shift of the absolute value to the right 3 units. Now let's look at y equals 2 times. Let's introduce the vertical stretch of 2. Why is that a vertical stretch of 2? Well, first of all, the pivotal point. Notice it doesn't change, right? Because the lowest it can ever be, y can ever be, is 0. And it's still at 3, 0. So that still stays the same. But every other y value, so this is going to go to 0, every other y value is going to get multiplied by 2. So this will become 2, this will become 4, 2, 4. And so that's kind of like our latest set of y values, and that's going to look like that. So same pivotal point, but it's got the slope of the lines here now are 2 and -2, where they were 1 and -1 before. So that's the vertical stretch of 2. And then now all we're going to do is add 4 to all these, right? Because so we're looking now at this thing here, literally we take our y values from here or from here, and then we just add 4 to them. So we'll add 4 to here, we get 8, add 4 here, 6, 4, 6, 8. So these are our final x, y values. So let's graph that. So it's literally taking that blue graph, it's taking this graph here, and just moving it up 4 like this. And so if we go, let's compare it to the original. Let's go back to y equals absolute value of x, and then the final graph. Notice that the pivotal point is at 3, 4, right? So let's just highlight that. So 3, 4 will be the location of the pivotal point. And the other thing to notice is that this 2 here, let me use another color, this 2 is significant because it actually tells you the slope of the branches. So you go over 1, up 2, over 1, up 2, and vice versa here. So 2 would be the slope of the right branch. But nonetheless, that's a very important key feature to help us sort of be more efficient at graphing. So now I'm going to outline some steps for graphing more efficiently. What we did on the previous slide was really took the transformations one at a time to understand how they work, how they operate, but we can do this more efficiently. So here we go. Start with the generic function. So a times f of x minus h plus k. And start by identifying the parent function. So we know, for example, in the previous example, we knew that f of x, the parent function was the absolute value of x. And either mentally or on paper, make a little sketch of that function so you kind of can help save time graphing if you know what type of symmetry that you're dealing with. Step 2 is to identify the pivotal point, and the pivotal point is, again, where does the function think it's starting? The function always thinks it's beginning when its input is 0. What value of x will make the input 0? Well, obviously, as we showed in the example before, it's going to be h. And when x is h, and the function thinks it's starting, the y value will be k. So once you find your pivotal point, you build your table based on this point. And for most parent functions, other than square root, you can just choose 1 or 2 values of x on either side of that pivotal x value, plug into your function, and work out y. For the square root function, you might as well begin the table at the pivotal point because remember, you can't have a negative under the square root. And one last thing. I'm going to help you to observe some key patterns, and by the end of the video, you won't even need to make a table. So stay tuned to the very last slide to figure out how to do kind of speed graphing. So here's our first transformation of a parent function practice. So what is the parent function? We see that we're dealing with a cube function and a cubic function, you could say, and that cubic function looks like this, got some nice symmetry, rotational symmetry going on about its pivotal point. What is the pivotal point? Well, let's just make sure we understand. First of all, that half is a vertical compression of a half, and then the plus 4 in the parentheses is shift left 4, and then shift down 5. So that's going to put the pivotal point at -4, -5. So we make a table of values now, let's put our pivotal point there at the center. And let's go a couple of values, sorry, on either side. So let's pick these. And I will work one of them out for you. So together we can do x equals -3. So if we plug that in, so y equals 1/2 -3 plus 4 squared minus 5. So it's 1/2 times 1. Sorry, that's a cube, 1 cubed minus 5, which is -4.5. So -4.5, and then if you would like to do the others, I'll just tell you what they are. So that comes out to be -1, -9, -5.5. Now, one very interesting thing you should note, this is why the symmetry is helpful. It's first of all, notice that this is an increase of 1/2. That's an increase of 1/2 there, and by the symmetry of a cubic function, it makes sense that this would be decreased by 1/2. And why is that 1/2 significant? Well, that's actually the same as the vertical compression, and that's going to be a sort of key feature we will pay attention to help us graph more efficiently. So if we graph the points that I worked out there, we get this. And then if we graph the final result, we see that the pivotal point, here it is, it's at -4, -5. And the other thing to observe, just briefly here, is that if you go over 1 here, you go up a half. But if you go 1 to the left, you go down a half, as illustrated in the table. For our next practice problem, all right, so this negative outside here, that's a reflection over the x-axis. For 3 will be a vertical stretch of factor 3. Notice that there's nothing with the x under the radical sign, so that's going to be the horizontal translation of nothing. And plus 2 is a vertical translation up 2. So let's go through. Parent function is f of x equals the square root of x, which looks like this. So the pivotal point is here. It's no special point of symmetry, but it's important for our table. So the pivotal point for the transformed function, well, for x, there's no horizontal translation, so that would be 0. And y goes up by 2, so 0, 2. So let's go to our table. Remember, for a square root function, you might as well start at the pivotal point. So we could put in x equals 1, so 2, 3, 4. We're going to realize that actually some of those don't work so well. So when x equals 1, y equals -3 square root of 1 plus 2, which equals -1. When x equals 2, that's just going to give me a decimal. I just can't be bothered to get my calculator out. 3 is kind of annoying. What about x equals 4? Well, I'll just do that one for completion. Square root of 4 plus 2, which is -3 times 2 plus 2, which is -4. So if we graph those points, the ones that just 3 points, that's all you really need to get the correct shape. And there we have the final graph. And now let's see what we observe here. Remember this, this value here, this -3. Notice in the table that that's how you get from the pivotal point to the next value, right? So that's down 3. Kind of exactly what that value of a is in front of the function. So notice that in each case we're just increasing x by 1, and we notice that y changes by whatever that value up here of a is. So here's our third practice problem. And what is the parent function? Well, it might be a little hard to sort of recognize here, but really there's nothing happening, right? There's no square, square root, cube, anything like that. Well, that's because we're just dealing with this parent function, a straight line. And we know that a linear function is going to look like that. Its pivotal point is at 0, 0 for the parent function. But the pivotal point for here, so we have, let's run through these again. We have a vertical stretch of 3. We have a horizontal translation to the right 5 and a vertical translation down 2. So that puts our pivotal point at 5, -2. If we put that in our table, 5, -2, well, because this is a straight line, I only really have to go one value on either side. And if you plug 6 in, I'll let you do that, you get 1. And if you plug 4 in, you get -5. And what we should observe, well, let's first of all graph that. So those are the 3 data points because it's a straight line. I only need 3 points. Connect them. And now we have some really interesting things going on. So remember this 3 that should appear in the table. Well, indeed it does. If x increases by 1, then this increases by 3. The y value increases by 3. What else should you observe? All right, well, 3 is actually the slope of the line. Let's look over there. So increase x by 1, you go up, y increases by 3. And you might recognize this form of equation of a line. So the 3 is the slope. And you might have seen it like this. Okay, let me write it like that. So it's point slope form in disguise, but you bring the y1 over. So plus y1. So the slope is 3. X1 here, x minus x1. So x1 is 5 and y1 is -2. So x1, y1 is the special point. All right, so in this case, 5, comma, -2 is when you do point slope form. When you write point slope form, you need to know a point that it goes through. So the line goes through 5, -2, and then you just need to know the slope, which is over 1 up 3. So for our next practice problem, the parent function is obviously x squared, a quadratic function, which has symmetry around the y-axis, at least for the parent function. And the pivotal point, let's go through these again. So the negative is a reflection over the x-axis. The 2 is a vertical stretch of factor 2. Plus 1 means shift left 1. Plus 3 out here is shift up 3. So therefore, we know that our pivotal point is going to be, so the vertex, which usually is at 0, 0, will go to -1, comma 3. So let's put this at the center of our table, -1, 3. Let's go 2 points on 2 values of x on either side. And I'll let you do the arithmetic, but if you put in 0, you should get 1. And if you put in 1, you should get -5. Now, using the fact that this is a quadratic is symmetric, at least over its axis of symmetry, we know that this is going to have to be 1, and this is going to have to be -5 to match up perfectly. The other way we could have, the other thing we should notice is that if you increase 1 here, you notice again that you go down by 2, which is the value of a, as we've observed before. And so let's graph the data points, and we have an upside down parabola. And once again, our pivotal point is at -1, 3. And here it's nice to see how you can see how it's symmetric about its axis of symmetry, which is why this value and this pair here, these y values had to match up. So for our last practice problem before the speed graphing, let's identify our parent function, which is cube root of x, which we recall looks like this, like a y equals x cubed on its side. And in terms of thinking about the pivotal point, let's just identify what's going on here. We have a vertical stretch of 4, horizontal shift to the right 2, and no vertical shift. So that means that the pivotal point is at 2, 0. So let's make that at the center of our table. And if you plug in, let's go 1 on either side, go 3 and 1 here. If you plug in 3, you'll get 4. Try it out. And by the symmetry, if I know that this has to be -4, now we also, without plugging in, we could have realized that the vertical stretch is 4. So if we add 1 to x, we would add 4 to the y value. And using the symmetry, we got those data points. Now, you could put an x equals 4 here, but it won't work out nicely because the cube root of will be the cube root of 2, which is not very pleasant. So what you try to do when you pick a value of x for a cube root function, so it's good to make the inside, make this something that we know the cube root of, which is like 8. And how could x minus 2 work out to be 8? Well, if x was 10. So if you pick x equals 10, and it turns out that cube root of 8 is 2, 2 times 4 is 8. And by using the symmetry, we'd also get -6, -8. So let's graph those points, and then let's connect. And once again, for the last observation, just to reiterate before we go into speed graphing, that from the pivotal point, if you go over 1, you go up 4. And that's going to help us in the very last slide. For our final activity, we're going to do some speed graphing. And notice I have all 6 parent functions here, and they all share the fact that A, the vertical stretch is 2. That's going to help us find our very next point after the pivotal point. They all share a pivotal point of 3, -1. So let's start graphing them. So for the linear function, 3, -1. And I know that once I get the pivotal point, I use that value of A, and I go over 1 up 2. And because this is a straight line, and it has that symmetry, I can go left 1 and down 2, and I connect, and there's my line. For the absolute value function, pivotal point 3, -1. For the very first point to the right, I go right 1 and up 2. And because of symmetry of absolute value, I know this point exists. And I can create the absolute value graph. The square graph, the quadratic function, so 3, -1, it's actually, the points are going to be the sort of identical. Those 3 points are identical for the absolute value, except that you know that the shape has to look like a parabola. What about the cubic function? 3, -1. Like the linear function above it, the symmetry is such that you go right 1 up 2 and left 1 down 2. But now don't just connect them with a straight line. You've got to add that little squiggle in. Square root function. So over 3 down 1, here's the pivotal point. Move over to the one right up 2. And I'm kind of run out of space there, but I know it's going to go something like that. And finally, the cube root function. So pivotal point 3, -1. Go 1, right 1 up 2. As for the linear, as for the cubic, because these are all kind of odd functions, left 1 down 2. And now I've just got to remember to do the squiggle like this. So there you go, speed graphing. If you only need three sort of points to work with, then that's great. Your teacher may ask you for more detail like y and x intercepts, but this is a great first start.
Congrats, you made it to the end of my video. Hoping that means you found it helpful, and if so, please do like and subscribe and check out more of my videos on my channel, Ready to Derive.